Here we go again, a review of cardiac output. On the graffiti page right here, notice that we have cardiac output defined as the, it is defined as the amount of blood that leaves one side of the heart per minute. And it's convenient to think about the left ventricle. So we can look at the amount of blood leaving the left ventricle per minute. That is the amount of blood entering the aorta per minute. And the equation for that is cardiac output is equal to heart rate times stroke volume. Now, in our simple cartoon person example, let's assume the person has a heartbeat of 75 beats per minute. Let's say the stroke volume is approximately 70 milliliters per beat, which is a very small amount. However, at 75 beats per minute, this comes out to be 5,250 milliliters of blood per minute, approximately. And if we convert the milliliters over to liters, then that comes out to be 5.25 liters per minute. Stop that. There we go, liters per minute, which again is approximately your entire blood volume going through the left side of your heart per minute. That's significant. Now, for the sake of holding people accountable for working with this thing right here, we won't necessarily throw numbers at you, although it's quite simple to do one multiplication. Instead, what we're going to do is we're going to ask you what's the most immediate and obvious effect if you change one of the factors inside this equation. If I just and only change the heart rate or just and only change the stroke volume, how should the cardiac output respond? Well, this chart right here takes the math out of the thing. So we're going to say if you increase the heart rate, then the cardiac output will go up. That's obvious from the mathematics up here. In the multiplication problem, if you make either one of these numbers larger, you'll make the product larger. If you make either one of these numbers smaller by itself, the product will be smaller. So we're saying what is the most immediate and obvious effect if you increase the heart rate? You would increase the cardiac output. Very direct. What's the most immediate and obvious effect if you decrease the heart rate? You would decrease the cardiac output. But if the one and only thing you did was increase the stroke volume, then you would increase the cardiac output. If the one and only thing you did was to decrease the stroke volume, then you would decrease the cardiac output. So on the graph right here, it says if this, then this will happen. Or if you want this to happen, do this down here. So you need to look it over and see if it makes sense to you. Again, we're going to consider one factor at a time because it's too many factors involved to be able to work everything out at the same time. In class, we'll use the word chaos to represent that there's too many factors involved to know what's going to happen. We can only do a one-step analysis. Here's another idea that's important, cardiac reserve. Cardiac reserve is the difference between the maximum cardiac output that you can achieve and your resting cardiac output. So here you are, couch potato, and here you are doing the best you can. Well, the difference between this and this right here is a measure of your athletic ability. And so for the normal individual, you might have about 4 times greater maximum cardiac output than you have resting. However, for an athlete, it's closer to 7 times. And you can recognize this feeling because if you have to exert yourself very, very quickly, it comes down to a matter of how soon do you wear out. If you can go from, like a sports car and just race up real fast, you've got a very good cardiac reserve. But for many people, they just can't do that. They just can't race their heart up very fast. Therefore, they're very limited. They get winded very, very quickly. Here's another couple of ideas before we drop this thing. Chronotropic factors. Chronotropic factors are factors that increase or decrease your heart rate. So chrono, of course, means time. And some examples of positive chronotropic factors include caffeine, nicotine, the hormones T3 and T4, sympathetic innervation, and the hormones epinephrine and norepinephrine. These all can individually cause your heart rate to go up. Heart rate to go down, well, parasympathetic signals will do that, and beta blockers will do that too. So again, these are negative chronotropic factors. These are positive chronotropic factors. Inotropic factors. Inotropic factors have to do with the force of contraction, not the speed of the heart, but the amount of contraction. And you can either increase or decrease that. Here's, of course, the idea about negative inotropic factors, but let's focus on the positive chronotropic factors, things such as changing calcium level, digitalis, T3 and T4 again, and sympathetic innervation, epinephrine, and norepinephrine. Well, to finish off the page down here, here are just some ways in which you can look at things that you already know, things that cause heart rate to go up and down, sympathetic and parasympathetic. Using this box and the idea of what's the most immediate and obvious effect, you can work it out. Here's stroke volume, and here's end diastolic volume and end systolic volume. And again, you can work it out. You can use the formula if you want to, or just know that if you have more end diastolic volume, you can have more stroke volume. If you have more to push, you can push more. If there is less end systolic volume left inside the heart chamber, that means that more got out. So again, you can think this thing through without having to use the formula. Down here is something that's a little bit more demanding, but how in the world would you cause your end diastolic volume to go up or down? Well, to get more end diastolic volume, increase venous blood pressure. If the venous blood pressure is greater, pushing more blood to the heart, then more blood will fill up the ventricle during that diastolic time. Another thing, of course, is to slow your heart rate down. And if you slow your heart rate down, you'll have more time to push blood into the ventricle between contractions. And of course, you can look at the other side too. For end systolic volume, well, to increase end systolic volume, well, increase arterial blood pressure. Make it harder to open the semilunar valve. The ejection period will be shorter and less blood will get out. More blood will stay behind. Decrease the force of contraction of the heart, and you'll push less, and so more will stay behind. Now, those are all pretty negative ideas, so here's a more positive way of saying it. For your heart to be more efficient, you want less blood to be left inside the ventricle. How can you do that? Decrease your arterial blood pressure. So this is why high blood pressure is sometimes problematic. Another thing you do to get more blood out and leave less behind is increase the force of contraction. And lastly, right here, the force of contraction. How in the world can you change that? Well, more sympathetic innervation will lead to more force of contraction. Less sympathetic innervation, less force of contraction. But stretching the muscle also has something to do with it. If you stretch the muscle inside the heart chamber, then it will react more forcefully and it will contract more forcefully. Now that's commonly known as Frank Starling's law of the heart. So if you balloon, say, the right ventricle out a little bit with more blood, it'll contract more forcefully. Same thing happens for the left ventricle too. So there you got it. Again, just a general review of some of the general ideas.